We have discussed earlier about the Phasor diagram for different type of circuit, for a purely resistive circuit, for a purely capacitive, and for a purely inductive circuit. And we saw there that the current, right, and the voltage, they are always in phase when the circuit is containing only a resistor. Okay. Similarly, when you talk about the purely inductive circuit, then we found that this current is lagging behind the voltage by an angle pi by 2. And for the purely capacitive, what we found is the current, okay, if this is the current, then this current will lead the EMF by an angle pi by 2. Okay, so here we have taking the the current to be along the x-axis. So that is how we get these three Phasor diagram, right, separately for resistive circuit, capacitive, and inductive circuit. All right. But here in this topic, we will talk about the Lcr circuit, which means a circuit that contains inductor, capacitor, and resistor. These three components, they are connected in series through an alternating source of EMF, E equal E naught sine omega t. Okay. Now, this L here stands for the inductance of this inductor, C is the capacitance of the capacitor, and R is the resistance of the resistor. Okay. Suppose at any instance of time, let's say the current which is produced by this alternating source is capital I. So this EMF E here will appear as a voltage drop across inductor, across capacitor, and across resistor. So now the voltage drop across this inductor, it is VL, and this VL is equals to IXL. Similarly, the voltage drop across the capacitor is VC, and that should be equals to IXC. The voltage drop across the resistor will be VR, and it should be equals to IR. Okay. Now, if this current here is maximum, so when the current is maximum, then I is equals to how much? I know. So in the maximum case, I will replace I by I naught like this. Alright? Okay. Now, this in this case, we consider that this potential drop across the inductor is greater than the potential drop across the capacitor. Okay, so please note down this point. And so, when you draw the Phasor diagram of this circuit, then you will get a circuit like this type. I mean a diagram like this type. Suppose I will take along x-axis as the current. Okay, so current is always along x-axis in this case. Now, for the resistor, we know that the current and the voltage, they are always in phase, which means if this is the directions of current, so this also should be the directions of the EMF or the voltage drop across the resistance capital R. Why? Because they are in phase. Alright, like in this case. Okay. Now, when you look at the inductor, we know that the current is lagging behind the EMF by an angle pi by 2. Which means if this is the current, then this would be the voltage which is acting in this direction, so that the difference between the angle between the two vectors is pi by 2. Here the current is lagging behind the voltage by pi by 2. Okay. Now, when you look at this capacitor, then we know that in the capacitor, the current leads the voltage by an angle pi by 2, which means if this is the current, so this should be the directions of VC. Okay. Now the length of this vector stands for the magnitude. Please, this is the magnitude of the voltage drop across the inductor. This is the magnitude of the voltage drop across the capacitor, and this is the magnitude of the voltage drop across the resistor. Okay. Now, because VL and VC are acting in opposite direction, so therefore the resultant of these two, it will be in the upward direction, that is VL minus VC. Okay, so this VL minus VC here, it is the net, or I can say the combined effect of the EMF between the two element, inductor and capacitor. So when you combine the two, you will get the potential will be acting along the the greater potential. Okay, so if you remember in class 11 we have talked about parallelogram law. So in parallelogram law of vector, what we have is if you find out the net resultant of this EMF VL minus VC and VR, then that net EMF will be acting along this direction. Okay, so this is my net EMF, and in this case, that EMF will be equals to, actually this equals to E, which is the net EMF, which is the supplied EMF in this case. But when we represent in Phasor diagram, we always take what? We always take the maximum value. Okay, so the maximum value of the net EMF will be acting along this direction. Okay, so if you drop a perpendicular in this way, okay, now look here. If this is equals to VL minus VC, then this side also should be equals to VL minus VC. And the distance from here till here, it is equals to how much? VR. Okay, now let us see that this net EMF, it is making an angle phi with respect to the current axis. Or I can say that the EMF, the net EMF and the net current, they are having a phase difference phi. Okay. Then, from this triangle, suppose I'll name this is O, this is A, this is B. So from right angle triangle OAB, right, this is the hypotenuse. OB is the hypotenuse. So square of hypotenuse is equals to the sum of the square of the other two sides. Or I can say just E0 is equals to root over VR square plus VL minus VC square. Okay, next, again E0 is equals to root over, instead of VR I will write I0 square R square, instead of VL I0 square XL square, sorry, instead of VL it is just I0 XL because I have no square, the square is outside. Instead of VC, I0 XC, and then outside bracket we have a square. So if you take common this I0, then you will get I0 outside the root, and inside you'll have just R square plus XL minus XC whole thing square. Or I can say E0 upon I0 is equals to just root over R square plus XL minus XC, okay, whole thing square. Now this E0 upon I0, it is EMF upon current. So we know EMF upon current is always a resistance. So, but the resistance in this case is not capital R. But when I say resistance here, it means the net resistance of the combination. Okay, so therefore the net resistance of this combinations of three elements will be known as Z here. And this Z, I'll tell you the name of Z. So this Z is known as the impedance. What is Z? Z is known as the impedance. So this impedance, it is actually the net resistance of the combinations of the circuit of the three elements. Okay, so this is how we derive about the net resistance of the three elements connected in circuit using a Phasor diagram.